Welcome and hello everybody to the course Crystal Engineering, Chemistry Beyond the Molecule. Have a look on me. Hello. Today we will talk about computational methods and the question is why. The answer is computational methods can help us to analyze serious crystal packing, molecular arrangement in solid state. And the main focus on the next minutes is which methods are really useful for this aim, helping us to understand more in solid state. Have a look. Well, the question is for us, what are the dominating, stabilizing, energetically intermolecular interaction? So it's not the question which kind of intermolecular interaction are present. The question is which are the dominating, stabilizing interaction. Well, this is our question. And the next question directly is, how can we calculate it? Let's have a look. Have a look here. We have seen this molecule in the last lecture. It is cyclohexyl phosphoric acid. Well, have a look here. You see several functional groups. And if you look to the crystal packing, you will see there are dominating hydrogen bonds between neighboring molecules. Okay, this is the question, this is the answer on the question dominating. But now the next question is, if you look once again on this molecule, which is the conformation of this here, the central unit of a molecule? What is the conformation of this functional unit in the molecule in the crystal packing? So this is the question, and now have a look. How can we calculate? Think about. Well, one possibility is to make a geometry optimization of a molecule. You can do it very easy. Gaussian, for example, is a very useful program. And then you will get very quickly this result. And if you look to the angle, torsion angle here, torsion angle, HOPO, yes, when you will get nearly a tetrahedral angle. Is this the question? Is this the answer on the question? Conformation of a functional group in the crystal packing? Have a look on the crystal packing by itself. And you can look here using once again mercury. This is on the file. And you see directly the torsion angle is not typical for a tetrahedral angle. No? It's not comparable to a tetrahedral angle. It is definitely the angle is enlarged. You see it is nearly planar. Going back here, you see the torsion angle is 150 degrees. Once again, compared with the geometry optimization, you see a big difference. And this torsion angle makes sense because if you look to the crystal packing, you will see the dominating hydrogen bonds are building a layer, which is impossible with the geometry optimization of a molecule. So this is a nice example, and I will show you some more where, for example, geometry optimization in the gas phase make not really sense. It's not helpful. Well, another example. CF3 substituted benzene. Question is aggregation of this molecule in the crystal structure. First, geometry optimization of this molecule in the gas phase. You will get two different conformations. Here you see the CF bond length is in plane with the molecule, the backbone, and here's out of plane. So you would expect with this conformation is expected. Yeah. Have a look at the crystal packing. This is the molecular structure in the crystal packing. You see it is nearly, not exactly, but nearly the conformation where one CF bond is in plane with a ring. So the less energetically favorable conformation you will find the crystal packing. Going on, looking to the crystal packing of this molecule. If you look in the literature, there's a very nice, very interesting contribution published in Crystal Grown Design, a very serious, very good, extremely good journal in Crystal Grow and Crystal Engineering, and authors analyze several crystal structure with CF3 substituted arenes. I don't know, 3, 5, 4, I don't know how many structure. And I found several times, I found such a face-to-face orientation of neighboring molecules. So, what I have done, I said, okay, have a look, calculate pp interaction of such dimers in the gas phase. And we stated out that exactly this conformation here, exactly not the conformation, exactly this motive of PP face-to-face dimer is really, show really high energy. We see it here, really high energy, and we said such high energetical contribution of such dimer are expected in crystal structure of CF3 substituted arenes. Yes? Have a look. Only on the crystal packing of this, yes, the first molecule of a series of CF3 substituted arenes. Only CF3 substituted benzene. Well, what you see is, this is the crystal packing. Have a look here. And look here, CF3, this is the crystal packing, no, this is molecular structure, sorry, and this is the crystal packing. And what you see is, or what you not see, I would say this is a better thing, you see no dimers face to face. Going back, no face to face dimers, definitely not. Okay, going on. Question is, how can we use it? Computational methods. Well, I and hopefully for you also are using Mercury to visualize crystal packing. Let's visualize crystal packing of this compound. So, hydrogen in this. Okay. So, in this situation, we have a CF2H substituent on the phenyl backbone. Okay? And the question is now, what are the dominating interaction of this compound and crystal packing? You know, you can use with Mercury, very easy, I said it several times, and you have this very nicely feature, you can say short context, show me short context. Yes, and then I can say please enlarge, expand all, what you get is something like this. Maybe a little bit better here with wireframes. No, better maybe capped sticks. Yeah, look to the central motif here. You see several intermolecular interaction. Here the H atom interaction with fluorine, with a hydrogen. Here the backbone with a hydrogen. And so on and so on. So several intermolecular interaction. Once again, what is the dominating intermolecular interaction? Several short CHF and CHP interaction. What are the dominating? Question to you. What do you think? What is your suggestion? So, I will show you one useful procedure, one useful approach. And the main information, the keyword is energy contribution in crystal structure. So in general, if you're interested in crystal packing, then have a look on energy contributions in crystal structure. It makes no sense to look to energy contribution in gas phase or only molecule. Well, what we are doing, we are using this method set, MP2 and so on. We can use, for example, Gaussian. When we take a crystal structure, what we are doing is geometry optimization of a whole crystal, so of a molecule in crystal packing, normalizing the CH bonds. And when we are define dimers. I will show you what I mean. Yeah? And when we calculate the energy of the intermolecular interaction of each dimer in crystal structure, in the crystal packing, and when we compare the energies of the dimers. Well, example. This is a screenshot of a crystal packing. There's a central molecule and several neighboring molecules. Okay, you can say this is the first coordination sphere of a central molecule. When we define dimers, so starting from the central motif, define a dimer with a green one, for example. This is one dimer. Or you have a red circle with another neighboring molecule, another dimer. So you can, this way allows you to define several dimers. When you can calculate the energy of the dimers, most attractive energies of these dimers, and these are results. These two motifs, dimers, show the highest energy of all dimers. Here are the values, round about -4 and round about -3.5 kilocalorie per mole. Yes. That means if we look exactly, this uses the sp3ch bond in the direction of the backbone, and here the CH bond in the direction of the backbone. Where a typical T-shape, in this case is typical T-shape, with a CH in the direction of the backbone. These are the dominating interaction. You see there are no significant fluorine or hydrogen-fluorine interactions. Once again, have a look on the mercury picture. This is exactly what I have shown you here. Not so nice, but nearly the same. Huh? See it here. Huh? Central motif. Maybe we can here leave it hanging. This is something like this here. Okay? Very easy. And 1, 2, 3, 4, 5, 6 intermolecular or short contacts. What are we dominating? Yes. Have a look. So I use such a red line for most attractive energies. It's exactly with two of them. With two energies here, dimers. And here is the result with one and with one. With two intermolecular interaction. These are the dominating. Okay. Next thing, if you use such approach to analyze crystal packing, we can learn several things about crystal packing. What we have done, for example, here, we analyzed crystal structure of several fluoro-substituted pyridines. Those are some of them, only some of them. And when we use exactly this way here, I've shown you, here, exactly this. No? So, and here are the results. Here, 3 minus Fp or 5Fp means 3,5-difluoropyridine. So this is 3-fluoropyridine, 3,5-difluoropyridine, 2,3,5-trifluoropyridine, and so on and so on. Okay. This is the column of energy. These are the primary interaction between the dimers. And here are the contact lengths. The lengths of the contacts. Okay, a lot of values. What can we see? What we see is, for example, fluorine-fluorine interaction have a positive value of energy, which means fluorine-fluorine has no significant energetical contribution. First information. Yes, you have huge numbers of fluoropyridines and all of them show no significant fluorine-fluorine energetical contribution. Amazing, but what is the result? That is a result. The next issue is only compare or have a look on the length of contacts is not a zero interpretation of interaction. Strange. Have a look here, CHN interaction. The shortest contact, if you look at two, compare with two values, this is the shortest, this is shorter length, but the longer length contact show a higher energy. Don't have a look only on the distance. Sometimes it works for an interpretation of a higher or interpretation of molecular interaction, but only sometimes. In this case, longer distance show higher energy. Yes? Okay. Well, next thing, very nicely, is in Mercury, in this Mercury crystallographic package, there's one feature which is calling uni-force field calculation. They calculate the intermolecular interaction using force field methods. This is not possible in this low budget freeware Mercury. You need the Mercury with a license, but in this case you can really nice interpret and analyze the crystal packing. For example, look to the co-crystal. This is a very nice co-crystal. By the way, is it ternary co-crystal? No, this is a binary co-crystal. The central motive, and there's interaction here with methyl resistinol, and it interacts with tetramethylpyrazine on both sides. See it here, and it's going on. Additionally, you have molecules of this pyrocene here interaction forming PP stacking motif. Low. Question now to you. What are we dominating intermolecular interaction? Think about. What do you think? We have hydrogen bonds. Yes, here. OHN, typical useful in crystal engineering useful hydrogen bonds. And we have this PP stacking motifs, face to face, very nicely. Which motifs show higher energy? What do you think? The answer is the PP stacking motif show a higher energy, not the hydrogen bonds. Okay? Very nicely. I'm coming now to the last issue, last method I will present you here in this video talking about computational methods. Very often in literature you will find, interpretation of crystal structure using bond critical points. What is it? It is based on quantum chemical theory calculations. Yes, what we see it here. There's two examples of alkyne diodes. Yes, you see it here. Two examples. And what's going on? What we're making, first of all, we start with a crystal structure and divide the molecules in quantum mechanical subsystems in atomic areas. Yeah? And then we look to the electron density and of a topology of electron density, and we look where the energy starts and where it ends, and where the next electron density begins. You see very nicely here the lines. Each atoms, or all atoms, are surrounded by surface, and through which the gradient vector field of electron density has no flux. This is important. There's no flux. Okay? And when we look to the saddle point here, is there energy in the saddle point or not? In this case, there's no electron density, and in this case, we have an electron density. Okay? And when we said, okay, where in this case here we have electron density and we have a hydrogen bond or intermolecular interaction, in contrast to this point, in contrast to this issue or sample. And if you have an intermolecular interaction, when we said, okay, we have a critical point. Well, that's it. I hope I could show you how important computational methods are in crystal engineering and how very, very important it is to use the right methods to help us or help you to understand a little bit more crystal packing.